Hi, my name is Flora Yellin from Kitware, and I'm going to be presenting our paper on concurrent band selection and traversability estimation from long-wave hyperspectral imagery in off-road settings. Scott McCloskey, Cole Hill, Eric Smith, and Brian Clipp all contributed to this work as well. This research was developed with funding from the Defense Advanced Research Projects Agency, DARPA. Off-road navigation is a challenging problem, and many techniques developed for on-road navigation fail when applied to challenging off-road environments. This paper focuses on traversability estimation in off-road environments, specifically using passive long-wave hyperspectral sensors. Such sensors differ from active sensors, such as LiDAR, which are more commonly used for autonomous navigation. For certain off-road applications, active sensors may not be available due to cost, weight, power, or other constraints. And in this paper, we demonstrate the feasibility of using passive sensors, specifically long-wave hyperspectral sensors, for traversability estimation in off-road environments. Because hyperspectral sensors can be costly, we focus on discovering the potentially small subset of bands that are most important for traversability estimation. Understanding how many and which bands have the largest impact on traversability estimation is necessary to inform the design of new, more cost-effective passive sensors with fewer bands. Our new invisible headlights dataset for off-road navigation with long-wave hyperspectral imagery will be publicly released to the community to facilitate future research and development. Our band selection method addresses the question of how to select the optimal small subset of hyperspectral image bands for a downstream task. In our case, we use the downstream task of segmentation. Our goal is to segment the traversable from non-traversable regions in a hyperspectral image. However, rather than using the entire hyperspectral image, we first apply a band selection module that selects a small subset of hyperspectral bands to feed into the segmentation network. We jointly learn which bands are most important for traversability estimation and train the segmentation network. Learning which bands are most important for traversability estimation will allow for the design of cheaper sensors for autonomous navigation. Note that our band selection module can also be applied to other downstream tasks and to other applications. I will now describe the band selection method in more details. We want to select a small subset, little n, of all big N bands. We pose the problem with the loss shown here. First, the segmentation loss is applied to HSI, which is the hyperspectral image that only retains small n bands. The band selection parameter W is responsible for selecting which of the original bands should be retained in HSI. This binary band selection problem is relaxed using the softmax with a scaling parameter that is adjusted as the training progresses. Initially, we allow each band in HSI to consist of the sum of multiple bands in the original hyperspectral image H. As the training progresses, the softmax approaches hardmax selection, forcing each band in H to consist of only a single band from H. The second term in the loss function is a regularization function that encourages band diversity so that H hat consists of little n unique bands. Our method is tested on the invisible headlights dataset that we introduce in this paper. The invisible headlights dataset is a new hyperspectral image dataset for autonomous navigation in challenging off-road environments during both daytime and nighttime. The dataset includes long-wave hyperspectral imagery, traversability annotations, and visual imagery of the scenes. Data was collected from 4 locations across the U.S. in various seasons and during different times of day and night, including thermal crossover. More details about the invisible headlights dataset can be found in our paper. Finally, we present experiments for our band selection method trained and tested on the invisible headlights dataset. We split the dataset into IH256 and IH250, which correspond to 2 different sensors with 256 and 250 bands respectively that were used to collect the hyperspectral imagery. For our experiments, we select only 5 of the 256 or 250 bands in the full hyperspectral image. We refer to our method as the concurrent method, since the band selection module and segmentation network are trained concurrently. We compare our method to several baseline methods, including the retraining method, which trains the segmentation network on 5 oracle bands that were selected by our method, the HSI method, which trains the segmentation network on the full 256 or 250 band hyperspectral images, the broadband method, which trains the segmentation network on the single channel or broadband image, the random method, which trains the segmentation network on 5 randomly selected bands, and the evenly spaced method, which trains the segmentation network on 5 bands that are evenly distributed across the hyperspectral image spectrum. Here we show some qualitative results from our method. On the left is a forest scene, and on the right is a desert scene. The ground truth annotations are shown in addition to the results from the HSI method, our method, and the broadband method. The HSI method uses all available information from the hyperspectral image and is able to achieve impressive segmentation results. Our method can achieve similar results despite only retaining 5 of the hyperspectral bands. In contrast, the broadband method, which uses one band that is the sum of all hyperspectral image bands, often fails to detect traversable terrain in the scene on the left and fails to detect non-traversable obstacles in the scene on the right. Some quantitative results are shown on this slide. For both IH256 and IH250, our method succeeds in selecting 5 unique bands that span across most of the spectrum, and we are able to achieve similar traversability estimation performance as when using the full hyperspectral image with only our 5 selected bands. For more detailed results, please see our paper. In conclusion, we've demonstrated the feasibility of using passive sensors for autonomous navigation in diverse off-road environments, achieved similar traversability estimation performance using 5 selected bands as with all 250 or 256 bands using our band selection method, and we've created the invisible headlights dataset, which is publicly available at www.kitware.com/IHDataset. If you'd like to find out more about Kitware, please visit our booth or our website. Thank you.